cover half of one of the chapters, so you get to travel and leave early and have sweet. But if you want to, you can distract me and go longer. Everyone be quiet. All right, so today we're going to talk about improvement techniques. And most of this will be fairly straightforward, except that we're going to try to dive a little bit into some Six Sigma concepts. Just out of curiosity, for my own benefit, how many of you have worked in organizations that are a Six Sigma mindset and talk about that routinely?
I've heard a lot of talk about it, but I haven't seen anything.
Okay. On paper. On paper? Okay. I've heard. Well, the reason I was wanting to know is to find out who I need to ask for assistance with, because I've done a lot of reading on it, and there's a couple topics I think are frequently overlooked with Six Sigma, and I'm going to attempt to clarify that to the best of my understanding for you guys today. So, we're pretty close to ready to go there, Jamie? All right. Let's go ahead and get started at it. So we're going to talk about improvement techniques. So recognize that there is not a single method or improvement approach. It is, there are many different recipes for that. And even in our body of knowledge from this test study book, it mentions that there's different approaches, and even on the Six Sigma approach, there are a lot of different subtleties with that. And so I just wanted to throw that out there that it is frequently, sometimes organizations or people start fighting about, oh, that's not the right way to do that. Be patient with that and get a better understanding what the other person is saying before you flatly say that's not the right approach. So with that said, with any improvement, you typically have some type of problem or issue that is motivating you to look at that. Sometimes people call these opportunities, a euphemistic way to say that instead of it's a problem, it's an opportunity for improvement. Some examples that the book talks about, and I've even seen as well. Communication can be one of those. Too much scrap. There's others in our book as well. So it is helpful if you can take this problem and clearly define it. Now there's two challenges going on while you're looking at this, is that in the quest for clearly defining something, you may get to the point to where you keep studying it instead of actually moving on to fixing the problem. So I want to encourage you to not delay excessively in the quest of understanding the problem. Interestingly, I saw in a poster at one company where they had their mindset was fail fast. So some of you may be of an engineering mindset where you want to make the perfect solution or suggestion before you proceed, and if you delay too long, you may actually miss that opportunity. So failing fast, the idea with that is not so much to become a failure as in not achieving anything, but it is the sooner you can try to implement a possibility, and then maybe you can learn from that experience. And then the trick is to not backslide after you've had that learning experience. So one way to define a gap, a problem, is to talk about the gap. And so there's an illustration in our notes that talks about showing two items. This is what is, and then this is our should be. Another way to illustrate this might be with just a simple bar chart. And so your gap is the difference between the two. And so this type of graphic is a quick way to communicate, here's where we should be, here's where we currently are, or it could be the opposite direction. Maybe this is scrap quantity. So in that case, this is what we should be and this is what we are, whatever the case may be. But illustrations are a great way to communicate that definition. One thing it is challenge with a project for Daktronics is that you want to try to state your problem in such a way that you can measure that. So in other words, if you don't have some type of response variable that you can quantify, it makes it much more difficult to decide what this gap is. Does that make sense? So one of the problems we are dealing with doesn't have a nice, tidy response variable, as I talked about. We'll get into that in design of experiments. But in order to measure something, you need to have some type of quantity or object to get that measurement from. All right, so the next thing we're going to talk about is the plan, do, check, and act. Sometimes you might see a letter S in the second place for study. Let's go ahead and draw a graphic for this. And the idea of this is sometimes it's called a wheel. And the concept with this is that you do this over and over. Let's go ahead and write our keywords here. Sometimes this is called the Deming wheel in some cases. So the plan, we're going to establish a goal. So the do is enact a plan. Bring action to it. Our check is to measure our results, analyze. Sometimes you see the word institutionalize in the act segment. Any comments from those of you that have used the Deming wheel? Any experience with that anyone would like to share?
I hear a lot of people say adjust rather than act. I think act, it's implied that you might have to adjust your original plan.
So we're going to add adjust. So that's the reason we have this wheel, is that you have this grand plan to solve a quality issue. You create this plan, you put it into place, you get some measurements, you go, oh, that wasn't what I thought I was going to get. And if you stop, then you really haven't, you may have actually made things worse. I've actually seen that where you tweak something.
So in the spirit of continuous improvement, adjust your plan, do it all over again, just keep going through it.
Another thing may seem obvious, but do not lose what you learned in the previous loop around. Does that make sense? So that may seem obvious to those of us sitting here just looking at this dry erase board, but if you are in an organization where one team member did the first lap around and they moved to another area, then the project is handed to you and you start doing the same thing. You can just, no pun intended, but spin your wheels, or your dimming wheel at that. It's also, I think, important to recognize that it looks remarkably simple, but to not discount it because of that. Does that make sense? So it's pretty straightforward. Next thing we're going to talk about are the reasons that continuous improvement are advantageous. So this, once again, is talking, comparing two different organizations making improvements. So let's say you are with company A, you are making improvement over time. We'll just make this some type of measure performance. But if another group B is proceeding at a more aggressive pace of improvement, they will overtake you over time. The other thing that is worthwhile to observe here is that if an organization is able to have some type of breakthrough, say this is group C, let's move them down just a little bit further. So over time, there might be a group C that comes into the market late with some just radically different method or product. I do want to emphasize that even in commodity markets that are stable, if someone comes in with a radically different method of preparing that or harvesting it, let's say if you compare harvesting grain by hand compared to a combine, a thresher, and then that first person that figured out, hey, I could have a self-propelled threshing machine. Maybe I'm showing my age a little bit. My dad actually had a pole type wheat harvester. So this is a rough crowd today. A lot of resistance. We'll move on to something even more exciting called Six Sigma next.
Called what?
Six Sigma.
Six Sigma is exciting.
All right, good. We got at least two of us in here that are.
Start reading about it, you can't quit.
Congratulations. I frequently even stop, at least to rest. All right, I may have said this before, but Six Sigma was, I recall, developed by Motorola, people that launched our mobile phones. Thank you, Motorola, for giving us smartphones, if you will. So, in that industry, why do you think Motorola was interested in this concept of Six Sigma? Does anybody know that off the top of their heads, or? I mean, our book talks about Motorola, but what was the motivation in
Even one part failure in the entire body will destroy the body result.
Right, and just loosely, how many components do you think are in a phone when you start looking at the circuits that are necessary to do that?
1,000 at least.
I guess maybe even more than that. I guess it depends on your definition of a component. When you have an IC chip sitting there, is that one component, or is it have components inside of itself that count towards that? All right, so we can just say that there's a lot, especially when you start looking at things like circuit board's fine, but maybe none of you have had this, say, the buttons on your phone don't work anymore. Display's fine, calls are coming in, you can't answer them. Or, I'm sure it's never happened to any of you, I had a phone on my hip one time and I thought it'd be fun to play some outdoor volleyball, fall, hit the screen. Phone still functions, you can't see what it's telling you. So nonetheless, there are a lot of things that are required to place a call, receive the call, receive that. So Motorola understood that you have to be very consistently good in order to get a functional phone. And not only that, but if you want to sell this to a bunch of other people and not have a lot of warranty claims, you need a high probability that your device is going to be sold or purchased by other people. So just very briefly, remember we talked about components in series. And if each one of these worked 90% of the time, the probability of the system drops to what if all three of those have to work? So 0.9 to the
73%?
70 what?
73%?
73. That's only 3 items, and Brian did that for me last time of like, what's 0.9 to the 10th power?
0.34.
Yeah. So, very quickly you can see how if you have to have all those components work, and you're in the thousands category, you're highly motivated to do that. All right. Next thing, concept of, we have our normal curve, our central tendency of that population, and then I think most of you recognize the concept of a term sigma, which is a standard deviation. So if you have a process that is performing at 1 standard deviation, what does that come out to? Well, that will be 68%.
You're going plus or minus 1, right?
Correct. So 1 sigma on one side is 34, 33 and change. All right, so that's where the term sigma is coming from. It's measuring the standard deviations. And we've already established that the probability of each of the components, 0.9 to the 3rd power is a small number, and as you get more, so it was determined that you want to get out to plus 6 sigma and all the way to the negative 6 sigma. So the interesting thing to me, for those of us that read this too much, I'll just go ahead and say it rather than holding you in suspense. It was recognized that processes vary as they're operating. Okay. So what happens is, let's say you have your tolerances set at plus or minus 6 standard deviations. If it's perfectly centered, you will only have I'm just looking this up for us. .002 ppm. Now where I'm getting that is that on each tail, 6 standard deviations away, we're going to have 0.001 out of a million in each tail. So total, we would lose practically nothing. But we need to recognize that our process is moving, and it's a common belief. I don't know how they decided this, but they base it on the idea that most processes will vary plus or minus 1.5 standard deviations. So now I'm going to attempt to draw another normal curve over the top of this. So if 1.5 is here, then it is possible that the top of my curve could sit there. I may also have so what I want you to recognize is that a process is typically drifting during manufacturing in that range. So if that happens, suddenly this, I'm not drawing this to scale very well, 1, 2, 3, 4, 5, 6, so way out here on the end, and that black one basically goes to a very small number. If you drift 1.5 standard deviations to the right, you will now have 3.4 out of a million failed or exceed the tolerance. Does that kind of make sense what I'm saying to everybody?
What did you say, 3.4?
3.4
Yep, per million opportunities.
per million. So for those of you that I'm sure sit at home and you read something and you make sure you calculate to match up the numbers, that's why it will be 3.4 instead of 0.002
Because of the drift of your process.
because of this drift.
But if it stays centered like the first one, then it's 0.002.
Correct. But have you ever
But it
seen
won't
it?
do that.
Correct. And that's the part that took me a long time to grasp on Six Sigma is it's not just the perfectly centered process. Those organizations realize that the processes are going to vary, and we want to recognize that our tolerance zone, we're likely going to have fallout on the positive, one of those two sides. Any questions about that? All right, I'm going to draw a couple other graphics, and then we're going to stop to do a in-class exercise about the Six Sigma that we'll turn in for homework. Now, some of the things that I'm putting up here are not actually in the book, such as this little explanation I did right here. So make sure you're clear on that. The next two graphics are not in the book either. Those of you that are curious about the book, I'm using this one from Breyfogle. I'll just write this guy's name up here. It's kind of an excessively big book. I thought it was kind of clever on the author's part to make the pages really narrow so it looks like a really thick book instead of using larger pages. What I wanted to show you in regards to, sometimes you might hear in the literature people talking about the sigma level or sigma quality level. So here's our ppm. I'll attempt to draw this fairly close. It's going to be so if we're at 1 sigma, and then we got here to 6 and 7. Around here, this is you're on a domestic airline flight. Probability of having a fatality on that is 0.43 per million. So what I want you to understand with this is if you have a perfectly centered process, it will follow that arc. Now the challenge is that when your shift happens, that pushes your failures or defects per million up and to the right. Actually, just up. So the other thing I want you to grasp from this is that if you, so let's say you make a 10% improvement on the perfectly centered process, you're not actually making a 10% improvement for the shifted process. Does that kind of make, let me redraw that for you. If you improve this by 10%, your drift is still taking place, and so it's not a linear relationship on that. Does that make sense? Ron buys that?
Yeah, I'm in.
All right. So, I thought it was I'll draw these up here and then I'll put them in a table format for you. So what we're doing here is I'm going to show you the points at 1, 2, 3, etc. sigma. So if you go from 3 to 4 on your sigma quality level, on the shift, at the maximum part of that drift area, that would be basically a 10 times improvement. Going 4 to 5, that is 30 times. Let me just write these here as well. So at 3 sigma level, that is at 66, 8, 10 parts per million. At 4, that is 6,210. Going from 5 to 6, that is 70 times improvement. And then trying to get to, must be off a number here. I believe I am is 3. 4 is 10 times. 3 is 66. 4 is 6,000. 5 is 233, and then here's our 3.4.
You're going 4, no more than 3.4.
Correct.
6 signal.
So the biggest thing I want you to get from this poor attempt at a table is to recognize that if you make a smaller improvement on when you're closer to the central tendency, that's pretty easy to do. But if you want to try to do that as you get further out on that curve, it really takes a very diligent effort to get to that point.
And a lot of money.
That's another way to put, and recognize that 3 out of 1,000,000 mistakes, like let's say max, just start thinking about how infrequent that is. So casual mistakes, you know, like, oh, Jerry forgot to submit that paperwork today. It doesn't take long to get to 3.4. So let's talk a little bit about the process that's attributed to Six Sigma. This is kind of similar to the plan, do, check, and act, plan, do, study, act. So there's different names for these, and I'm going to use the ones that are in our book not to confuse things too much. So I'll write the initials across the top. First one is letter D, so we're going to define. I'll give more explanation for each of these. Define, measure, analyze, improve. Control. So here we're going to define our customer. CTQ stands for critical to quality traits issues. So we want to know what the customer is expecting. So the measure phase is where we're going to collect data and information. Analyze is where we're going to look for those gaps between our expectations and what's actually taking place. These are where we do a lot of statistical analysis, hypothesis testing, things of that nature. Improve is creative methods or new ways of doing things. Plan to prevent backslide. And there's more to that if you are interested in it. There's also another author that's shown at the bottom of our notes that has a slightly different view on that. Then if you look at this Brayfogle book, he's got yet another set of names for that. But key things you're typically going to see is something about the customer and what those expectations are. You need to collect information, observations, plot that, make statistical inferences from it. And then this is these last two I think are some of the more challenged ones. Once you know what your data is telling you, how do you actually implement an action as a result of that data? And then the last one's not easy either, to prevent backsliding, because it's easy for organizations to revert back to the way they did it previously. Now, the other thing, I'm not going to actually write up here, but there are different levels of, you may hear the phrase black belts or green belts. ASQ does provide certification in that, and the reason I'm mentioning that is prior to ASQ getting into it, I believe that most of the other certifications were performed by consultants, and private companies would knight that person or present that black belt after a couple weeks of training. And so I got, in my opinion, that's kind of skeptical, because I don't know that the same rigorousness was applied to all organizations that ever performed that type of certification.
Yeah, I know a lot of individuals, used to work with a lot of individuals who, their company created their own programs, their own ways of certifying, so they'd call themselves green belt or black belt, but it was in accordance with Motorola's standard or maybe Sanmina's standard.
And the challenge, as you mentioned, is it doesn't mean that just because someone's a black belt, it means that they're not capable, but there are a few that I think were not as rigorously screened for that opportunity.
Specialists in their industry probably not schooled on broad knowledge base.
Right, so for example, the body of knowledge for Six Sigma is remarkably similar to the CQE. It just adds the concept of financial responsibilities with that. So in other words, what I'm trying to say with that is that Six Sigma does emphasize the financial prioritization of projects. So in other words, a CQE body of knowledge does not emphasize that you're going to actually save money by directly making that, whereas a a Six Sigma black belt is frequently challenged with being able to save a significant amount of money. And what I mean by significant, I'm talking about hundreds of thousands of dollars. So some certifications actually required you to save a threshold value of dollars before you could get your certification. So those of us that work in the South Dakota area, if you're working for a company that only has $1 million in sales, how are you going to be able to save $500,000 in costs? It's just not possible. So I do appreciate the ASQ has changed the requirement for ASQ does not have a financial threshold that you have to obtain to for your portfolio.
Yeah, I got a little certificate to put on my lovely wall for that because it was a financial goal, and I used it to find, measure, analyze, improve, control to as an approach to reduce excess and obsolete material. So I think week one we talked a little bit about, I said why I'm here, because I've embraced quality management. I've never worked inside of a quality function. But these tools can be applied in lots and lots of different areas if they're appropriate for the problem you're working on.
And one thing I'd like to add with that is that some organizations view that as, oh, that's quality's issue to attack that, and it's very unfortunate if an organization does not recognize how the tools can help them.
Yeah.
And another thought I'd like to add with that is, even if your role is not in the actual quality function, it's still helpful to understand how these improvement projects are motivated, funded, and how to make the improvements stick. All right.
Are you going to talk about COPQ?
That initial is not.
Cost per quality?
Oh, okay. Yeah, that is in a different chapter than this one.
Okay. All right.
I believe that will be 2 weeks. Maybe we'll
I like
do
to
that.
connect to the two because I've known people who do not want to spend the money on a quality management system to go from, say, 2 Sigma to 3 Sigma. They say it costs too much. I got to hire quality engineer. I got to hire quality technicians. And that just tells me that they don't understand COPQ. Because if we're spending a lot of money out the back door because we don't understand the cost of poor quality. It's not just on the shop floor, it's in our business processes, it's in our design process. Most of it, I don't know, most operations I've worked in, we've got rework designed in our production processes. We got places where we plan on fixing things as we build it. Motorola, and now a lot of things have changed in the industry, but Motorola, when they went on their Six Sigma journey, they once they finished it, they said we underestimated the cost of poor quality, and we estimated it at 40% of sales.
So stating that another way is 40% of sales was not a big enough cost.
They
did
said
not.
they underestimated it. They hesitated initially when they started their Six Sigma journey. People told them, well, you're I don't know how many billion-dollar-a-year company they were, but they didn't believe that 40% of their sales was not going to their bottom line because of COPQ. When they finished their journey, 4 or 5 years later, they said, I think we underestimated it. So when I hear decision makers say, I don't want to hire a quality technician, I don't want to put in an automated system, I believe that those folks have not been trained on the cost of poor quality.
And the other challenge with that is that some of the quality costs are kind of hidden or not easily, like if you scrap something, is it just the cost of the item that you paid for, or the lost opportunity to administer that?
Yeah, that's how you what you consider the cost, and there's a lot of it out there that we don't consider as a cost of poor quality.
All right, so what I'd like to do next is the project I'm going to, that's on the Dropbox. So we'll put that up here on the screen. So while this is loading, I'll go ahead and verbally tell you what that is. So I want you to describe some type of process. And if you're not in class, that could be cutting parts or something like that. But I'm even suggesting that we can do things such as many of us have a cell phone that has a stopwatch on it. And what you can do is your process is do a start and stop on that cell phone on your stopwatch, and just write down how long that takes. So that will create a process. They'll have a number for that. So I want to measure 25 observations, determine the mean, standard deviation, and then recommend a tolerance based on that Six Sigma concept. So this is kind of driving at this thinking about what tolerance zone you would recommend for a process. Now, this is part of that chicken and egg question that frequently comes up on design. Do you set the tolerance and then manipulate your process, or do you make parts, determine what the natural variation is of that, and then set the tolerance after that? My contention is that it's better to maybe kind of do a little bit of both, but to set tolerances without thinking about what the actual process is very short-sighted, maybe. And then to recognize that processes drift. I mean, when people think of plus or minus Six Sigma, I think most people just assume it's going to stay centered all the time and not move, because they're probably doing some SPC, and they hear the word process control, so they think that that means it's locked in and doesn't drift on us. So, everybody kind of comfortable with what I'm suggesting for? Nope? All right, so I'm going to encourage you to measure 25 units of, or objects or unit of time. If you have a pretty good idea of some numbers from work, you can use those. I want you to estimate the mean and standard deviation. And then, based on what we talked about with the Six Sigma, what would you recommend as the tolerances on this process that we're going to do in the class? So like I said, one way to get numbers very quickly is if you have a stopwatch function on your cell phone. The process could be starting and stopping that. And just write down 25 of those. Find the mean and standard deviation. And then recommend what would be the range on it. So, one thing to recognize on the stopwatch is that you're going to, well, I won't tell you. Does anyone know what the, if you're very quick, what is one of the, what's the left end of that tolerance going to be? It's going to be 0, and why? You can't go into negative time. All right, so as you describe your process and think about setting your tolerance limits, recognize and suggest practical limits for that. All right, need more help, or can we just start getting 25? So what I want you to turn in for your homework is 25 observations. What is the average? What is the standard deviation? And then I also want you to describe the process. So it could be cutting something to length and measure it. You know, don't make the process more difficult. I want you to go through the steps and to think about what that tolerance would be. So I'm available to answer your questions. Let's try to accomplish this in maybe Maybe 20 minutes? Go ahead.
Okay, so this is good.